Alright, so let's talk about trig substitution. Alright, that's that first step we did when solving the equation of a circle. Solving the integral of the equation of a circle. Substitution. So what do you think it was? It was probably the substituting cosine or sine, whatever we did, into that equation. So how do you know when to use trig substitution? I know we know the double angle formula, and trig substitution should make sense. It just means plug in cosine instead of something else, but there has to be a sign when to use it. It's not like, hey, I'm doing this integral of x dx, and I'm thinking, no, I should make x equal to cosine, because that will make this whole problem easier, won't it? And then I'd have to plug in dx as inverse, no, not inverse cosine, wow, negative sine theta. Yeah, look how well this is going. This is already despicable. No one would do this in their right mind. Oops, I have to switch colors. All right, cosine, sine. So we'd have to plug in a negative. Wow. Yep. You'd have to have a negative cosine theta sine theta d theta. So you can already see going this way is silly, because this way would be easiest, just x squared divided by 2 plus a constant. But this is the route you're probably thinking of going, and that's no good. So we know it's not those scenarios, and we know that maybe involves 1 minus x squared. Yeah, we know it has to somewhat take that form, but there has to be like some sign, all right, from the underworld that know what you should do right now? Trig substitution. So this is what we're going to talk about in this video, and I'll try to see if I can come up with a problem or a few problems that would include it properly. Not like just made up junk, or not just basic formulas that you're only going to come across once. I want something with a little more substance. Maybe I'm not going to give anything. So let's see where we're going. So we know that if we take a circle and we have this angle, all right, of theta, we can make a variety of triangles with it. Triangle number 1 is this guy. Easy peasy. And what's great about this guy? This guy is exactly cosine if this guy is 1, and this guy is exactly sine. All right, that's one we could do. Ooh, know another? We could jet a line that connects with this line. So this red line from the center to here happens to be secant theta. I'll explain that in just a second. And this guy is tangent theta. And this guy would be 1. If this guy is 1, that means what we did is we took the smaller triangle and divided everything by cosine. Yeah, if we divide this guy by cosine, it turns into 1, which is what we see. If we divided sine by cosine is tangent. That's by definition. And if we divide 1 by cosine, well, that gives us secant. That's also by definition. And then there's one more triangle we can make. Or I only show it just to give a full description of these problems. Well, if we divide everything by cosine, why don't we divide everything by sine? So if we divide this length of sine by sine, we get a full length of sine right here. So this length is 1. Guess what? You just extend this green line to this extended line. And so what you'd find is that this length would correspond to cosine. And so it would be cosine divided by sine happens to be cotangent. Happens to be sounds like it's not true. No, it is definitely true. It gives you cotangent, which is just the reverse of tangent. That makes sense. Sine over cosine flipped over is cosine over sine, which is what you'd get there. Guess what this length is? It's the last one there. It is cosecant. CSC theta. You probably don't see that. But that is this length from here to here. All right, so we have 3 triangles. And because they're right triangles, they have a magnificent property. Let's write 1 cotangent theta. Let's just draw them out. And cosecant theta. Let's draw the one in red. Oop, there you go. And I'm not going to draw the one in blue. You're too used to it. This length is 1. This length is secant theta. And this length, height, is tangent theta. Alright, and you get the blue one. And I'll draw the blue one anyway. It's all about defining one side as 1 and seeing what happens. So we define this side as 1, this side as 1, and the hypotenuse as 1 as usual. And the hypotenuse as 1 is the most useful, and it creates a simple circle, so it's really easier, much easier to understand than the others. But whatever. So you can see that if this angle were close to 0, cotangent would go off to infinity, which is what you'd expect, and tangent would go off to close to 0, because it's getting really close to 0. Or if you go close to pi over 2, a quarter of rotation, then this tangent value would go off to infinity. Same with secant. And cosecant would go off to infinity at a value of close to 0. All right, so we've established that. So just using Pythagorean theorem, we can write these formulas, all right? So cosecant, this guy, squared theta is equal to 1 plus cotangent squared. And so that is one case. All right, secant squared theta is equal to, this one you've seen a lot, 1 plus tangent squared theta. Is quite useful to use, but it really comes out of this guy, which is 1 equals sine squared theta plus cosine squared theta. I did that kind of backwards. I want to do cosine first, but you get it. All right, so these 3 formulas are the reason why we use trig substitution. It's because they have a simple pattern, which is not only squaring, but hey, you could rewrite this in terms of square roots. By square rooting this side, you get square root of 1 plus cotangent squared. So if you ever see something in that form, 1 plus something squared with the square root of it, guess what? Cosecant or secant has the same pattern, is your person. Usually people choose secant because it has the exact same form as cosecant. Yeah, honestly, it's cosecant and cotangent. Like, they're both co, so it's like, it's clear that people don't really use them that much. So these are your 2 kings as far as trig substitution goes. So let's rewrite them and see what they'll look like if we rewrite them big time. All right, so we have, let's set up our regular triangle. So we have an X, we have a Y, and we have an R. So we know that 1 equals cosine squared theta plus sine squared theta. Cool, and this angle is theta. We know that secant squared, and remember secant is just 1 over cosine. So secant squared is 1 over cosine squared. 1 plus tangent squared theta. And really, you get the same result if you divide everything up here by cosine squared theta. It turns into that. Makes perfect sense. But let's treat them as 2 separate things for a second. So if you square root this gentleman, you get secant theta equals square root of 1 plus tangent squared theta. Cool. Now, what's great about that? Tangent is a relationship. Tangent of theta, in this case, is equal to this y over x. Y over x. Ignore the squaring. That was jumping the gun here. So you see that? Y over x. So that's one fact. And so if you plug in y over x into this formula, you get square root of 1 plus y over x squared equals secant squared of theta. Secant is inverse cosine, so it puts the hypotenuse on top and x value on bottom. So it would be r over x. I'm not even going to write it out to the right. All right, and so we're almost done here. Let's multiply by x. So we get r x square root 1 plus y squared over x squared. And now, this is the finishing touch. We bring in the x. So we have x times 1 is x squared. We have y squared divided by x squared multiplied by another x squared just gives us x, this guy. And so if you see something in this form, really ignore the fact that it's x and y and r. I just chose those letters. This could be many different scenarios. And you could even back it up a few steps to this guy. If you divide both these sides by 1, 1 over secant squared is cosine. Theta equals 1 over 1 plus tangent squared theta. Guess what? If tangent squared theta is this guy, y over x. Ooh, I'm a tangent, just not tangent squared. Then this is 1 over 1 plus y over x. Let's just keep it y. Let's say x is 1, just for this chance. This would be y squared, and that's equal to some function. Now let's call this one y and this one x. So if you see something in this form, that means when you take the integral, you want to take the integral of cosine here, don't you? Cosine would be a lot friendlier of an integral to take than this guy over here. So it's all about converting between these. All right, there's no stop to it. However, it's not as easy as just simply plugging in tangent, because you have to plug in its derivative when you use these formulas. That is just part of the integral process, plugging in the derivative. Can't do an integral without a derivative. So these are two things you'll see: a square root of something added to something, or 1 over 1 plus something squared. Or you could also see it with a square root. That's also common. So many forms. But usually square root is the kicker that makes it feel like an impossible problem. Until you have this friendly, not so friendly guy over here named trig substitution. Alright, so we said that one. And of course there's the easy one that's derived from this guy, which is if you make this x and 1 could be the r value, sure, you get, I don't know, either way you get something along this form, r squared minus x squared, right? And so if you're integrating something like this, that's not so friendly. But if you rewrite this, you get 1 minus sine squared equals cosine squared, or vice versa. 1 minus cosine squared equals sine squared. And then if you square root, then sine theta equals 1 minus cosine squared theta, all under a square root. Just rearrange it, see what it looks like. Trust me, it looks like that. So if you see a radical, the square root, plus something squared, so some a plus an x squared, maybe you could put a bx squared here, make it look even more impossible, then that is an indication you should probably use tangent, all right, because you have that plus sign. Now if you have something more like a minus bx squared, you should probably use something more along the lines of cosine or sine. They're pretty much interchangeable because, as you can see, the formula is pretty interchangeable. So that's kind of your ticket in the door. Now that doesn't mean that these problems are friendly. That just means they're possible, which means a lot for mathematicians, not so much for you. If you think something is possible, you'll still probably hate it. And this is one thing that is very easy to hate. And so let's try, let's do 2 problems, all right? Let's do one. I like this problem a lot for some reason. Let's make this guy 2 dx 1 plus 4x squared. How might I integrate this guy? Well, because it's 1 here, there's no simple, I can't plug in a logarithm or anything straightforward. It's not that easy. So we see this 4x squared, and we're thinking in our heads, you should be thinking, that reminds me a bit of this guy, 1 plus tangent squared. And 1 plus tangent squared also is secant squared. So if you have a square root anywhere, that really simplifies the square root. You get the idea. So we want 4x squared to be equal to tangent squared. All right? True? Yeah, that is true. If we can get that in terms of tangent, we'll be happy. And you'll see this will simplify the problem big time. So let's take a square root so we know what we're actually replacing. Square root of 4x squared is 2x tangent theta. So that's our actual derivative we're doing. So take the derivative of this guy, it's 2dx. Take the derivative of that one, it is 1 plus tangent squared theta. You should be like, ooh, wait, maybe that was a good idea. Maybe it is a good idea to make this problem a little more complicated, because you'll see what happens. This one's good. And it really just falls out of the definition of the inverse tangent derivative, but you'll see. So we now have the integral. So we have to replace 2dx. Hey, we have a 2dx with 1 plus tangent squared d theta. 1 plus tangent squared theta d theta. All right, and now we can replace 4x squared with tangent squared. So 1 plus, now rather than 4x squared, we have tangent squared. What's magnificent about that? Well, this guy, what is that? That is 1. Couldn't write it more clear. So the integral of 1, d theta, is just theta. Ooh, that's awesome. Oh, and then plus the c because we didn't put bounds on this guy. All right, and now one less step of simplification. We want in terms of x, because putting theta is meaningless at the moment, because only we know that we plugged in theta here in terms of tangent and stuff like that. So we know we have to do inverse tangent to get theta by itself and replace it with something in terms of x. So you can see it. Tangent, inverse tangent of 2x plus a constant is the integral of this one. 1 plus dx. All right, check that out. So sometimes it's pretty friendly like that. Let's try another, and then we'll conclude. So the integral of, integral problems, again, not usually easy, especially because you have to work with derivatives and basic integral rules at the same time. So the integral of, let's do, this one is difficult. 1 minus x squared. We're probably not going to solve this all the way, and I don't want to spend the whole day solving this either, so yep, there you go. That one sure is friendly, isn't it? The answer is no, it's not friendly. Actually, before we continue, I want to see if I can fix that guy up. Let's multiply the top and bottom by square root of 1 plus x squared. If we do that, this guy on bottom goes away, doesn't it? No, the square root goes away. So we get 1 plus x squared. Ooh, that looks very similar. And then on top, we get 1 minus x squared in a square root plus 1 plus x squared. So that gives us together 1 minus x to the 4th. Oh, yeah, that didn't help us out very much, does it? No, I don't think so. I thought it would. Doesn't really. Hey, but now you know you can convert, kind of. Alright, if you didn't see what I did, don't worry about it, because we're going to do some substitution. So, we see this x squared minus x squared and then a plus x squared. What do we want to get rid of? Well, this is why it's hard. It's because you could do cosine, but if you do cosine, this guy doesn't reduce, because cosine isn't of that nice plus form. It is usually with a minus. Cosine and sine are. So I'm gonna use tangent. All right, tangent again. I don't really want to, I'll admit it, but I'm using tangent anyway. So let's set 1 plus x squared. So let's set x equal to tangent. That's kind of nice because dx is not really nice at all. Is 1 plus tangent squared, or let's write it as secant squared theta. I also don't like writing secant because secant is just cosine. But the reason I write secant is because of tradition, probably. So now every time we see an x, we can replace it with tangent of theta. So this integral, ignore this middle step because we're not keeping that anymore. Yeah, it doesn't help us at all. So we have 1 minus tangent squared theta. And then on bottom, we have secant. We have 1 plus tangent squared. 1 plus tangent squared is the same as secant squared, and square root of secant squared is just secant. Ooh, that's nice. And last, the kicker, we can replace dx with secant squared d theta. Secant, that's the edge of the page. Secant squared theta d theta. All right, and now we can continue from here. The integral of those secants somewhat cancel out. We're left with 1 secant, or let's just write it as 1 over cosine. You can see that one of those secants goes away, so that's good. And now on top, we have not so friendly of a equation to solve. Tangent squared of theta. So how do we solve this? Well, this just requires good practice. So I'll probably end it as soon as I give up with this equation. I didn't realize it would be so annoying. Frustrating. So 1 minus tangent squared, with that could be 1 minus sine over cosine. And then you can multiply the cosine. So cosine squared theta. And that'd be minus sine squared theta. And that would be all over cosine squared. Do you see where I'm going with this? That should be the same thing. Yeah, it is. Just doesn't look pretty. That's all square rooted. That's divided by cosine theta. And so by doing that, this problem got harder. All right, let's just write the last step, this step so far. And I recommend you try it for yourself. Cosine squared minus sine squared theta. That reminds me of something. That reminds me of cosine of 2 theta. Cool. That's a little nicer and easier to comprehend. Then we have square root of cosine squared, which is 1 over cosine squared. 1 over cosine. And 1 over cosine times another 1 over cosine is cosine squared on bottom. Hey! That looks edible, in a sense. So we have cosine 2 theta, square root of that, divided by cosine squared theta. And we're just integrating that guy. Let's graph it to conclude. All right. So we started out with a very ugly function of 1 minus x squared divided by square root of 1 plus x squared. So that gave us a little hill in the middle. Let's make this bounds a lot smaller. Let's make it about 3. All right, and let's make this y value a lot smaller as well. Let's make it -3 to 3. So that's what our function originally looked like. Just kind of a lightly sloped hill. And we converted it to square root. Hopefully you can see this okay. Square root of cosine 2 theta, or 2x in this case, divided by cosine x squared. That value is squared. And let's see what this guy looks like. What? Oh my gosh, what in the world did I make? I've made a monster. Anyway, hey, that's good. It's interesting. Has some weird behavior. Let's remove this guy again. Let's take another look at that one. Yeah, that's bizarre. Yeah, maybe this was a bad idea. But hey, it does look easier to integrate, doesn't it? Hey, I think that's all we needed, all right? Just the confidence to finish this problem. And I don't really have it, so I think I'll call this good. But trig substitution, hard to do well. And the reward is very meager, and so I would be surprised if you have a good time with this. Thanks for watching.